Okay, good morning to everyone. Good morning to those colleagues connecting via streaming online. Today we have a seminar by Professor Michel Campillo, one of the most important seismologists in our international panoramic view. And the introduction will be Massimo Cocco, and the discussion also will be moderated by Massimo. Thank you.
Thank you, Paola. So it is a pleasure to welcome and introduce Michel Campillo. He's a colleague and a friend. We knew each other since almost for 35, 36 years. So Michel is an emeritus professor at University of Grenoble. He's also members of the French Academy of Science, and you are also a Chevalier of the Légion d'Honneur. This I didn't know. I just discovered for preparing the introduction. And Michel made investigations on many different topics from earthquake dynamics, which is where we interacted, but also pioneeristic work on the scattering of seismic radiation. And in 2004, he was opening a new window in the approach, proposing the cross correlation of the ambient noise as a measure of the state of stress and the velocity perturbation of the shallow crust. He also won 2 ERC grants, advanced grants, that were both dedicated to this ambient noise correlation. And also he was awarded by the Benno Gutenberg Medal at EGU, and you also EGU, and also you received the Gutenberg lecture for AGU. And personally, I believe that I always recognize that Michel approach to have a vision beyond the state of the art of the research. But what characterizes Michel's approach is his capacity to join this vision with a pragmatic and realistic approach to research. So he was not just in thinking, he was proposing methods and approach, essentially relating the theory with the data. And as a person, he's one of the easiest person to collaborate with that I never met in my career. So it is really a pleasure, Michel, to have you once again here. And please, thanks for your lecture.
Thank you very much for this introduction. Yes, perfect, thank you. Yes, it's a pleasure to be here, and I'm honored to participate in this seminar for the anniversary of INGV. I will talk about a story that is a part of ambient noise, as Massimo just introduced, and also monitoring. And this is what I have been interested in the last year. And I would like to share with you a series of points. I will not enter into much details, but to make a tour in a way on what we can do. And of course, it's not a review paper. It is really focused on some work that has been done by our group in Grenoble. I apologize for that. It is the point. And of course, I will present work that has been done by several researchers. Some of them are listed here. So, to make the point, we just mentioned by looking at the beautiful seismicity map that are produced just at the end of the corridor here. We see the big difference that occurred during a professional lifetime between the type of work that we were doing when we started, my generation, Massimo generation 2. This was the pre-INGV type. We were thinking of a problem in which the problem is the problem of a purely elastic medium with a pre-existing fault, and the medium is slowly loaded, and the earthquake problem is the problem of dynamic crust propagation, initiation and propagation. And of course, it's led to a lot of okay. And so it's led to a lot of useful models that allow to understand a big part of the data, to quantify the earthquake, and so it's not negative. But today, the data are showing a very different story. What we have seen in the last day, I mean, pushed by observation, of course, that the existence of transient instability of deformation on various time scale and the slow slip events are typical of these things. We have been also clearly pushed to consider the interaction with fluids at a different level in the crust. And recently we have the Noto earthquake that was really typical of this. Also the progress in describing the seismicity, and recently we have these deep learning advances that allow to describe the fault are systems. Systems at all scales, and very far from the ideal fault plane that we have in mind long time ago. And also we have seen that environmental forcings are important too. And for example, the precipitation loads can be related to seismicity. So the idea that the crust evolves on various time scales. And this observation actually points to the need to develop specific tool to detect this change, to measure the amplitude of this change, and eventually to image the temporal changes in the mechanical property of the crust. And of course, when we are talking about the crust, we know that for the earthquake problem, for example, everything in a way is driven from below, so we are talking about also the deep crust. And I would like to insist on that. So it's not a new idea to use the seismic wave to monitor. It has been done for a long time, and using different type of source, natural or controlled source, with a lot of success, but in the same time a lot of problems, mostly related to the energy of the source for the controlled source, and then the penetration of the wave, the repetitiveness of the source. This is true for the earthquake, for example, the frequency content, and so on. And so what we need is a method that can be generalized to a wide range of acquisition systems, in particular to the regional networks, as the one you are running here. Because these networks are producing a huge amount of data that are available today over a long period. And what I suggest here is that we should put more emphasis on using this data. Of course, it's extremely useful to have specific operation on particular fault, but as you know, the earthquake occurrence is something that is difficult to not only to predict but even to foresee on the long time range. And I made this specific remark here that to be overly specific, we as a seismologist, and especially for a seismologist like me, that is emeritus now, is that we have not to be in operation that could be the seismological version of the the desert of the Tartars. And if you know the story, you understand what I'm talking about. So my talk will be about the development of monitoring based on ambient noise itself. So the part one that will be the main is the noise-based measurement with a few stations, with no requirement about the number of stations, the density of the array, or so on. Of course, now we have also data from dense array that open new gate, and with recording for increasingly long period. And so there will be shorter part two, that is, can we do repeated scattering imaging with noise and array data and array processing? And the part three, can we use identified entropic sources that are repeated and dense array to end up with possibility of long-term monitoring? So, ambient noise seismology, I will not describe it at length, just to remind you that the idea is to use the correlation property of ambient noise at several stations to generate virtual seismograms that are the seismogram you expect if you have one source at one station and you record at the other. And this is a technique that has been developed technically for the processing and so on, and we have a lot of application of it. Just to show you a typical example of a clean processing, this is data from the US array. You see on very large distances, you can produce virtual seismograms, and here it's the long period relay wave, and then you see that we have the causal and causal version, but it works very well. You can make snapshot of the noise correlation, and you see the waves that propagate exactly as if there was a source at the reference station, that is the star here. And from that, we can make imaging, and this is the first example of this imaging that we produced with Nikolai Shapiro in California. But of course, the idea would be to use this principle now with monitoring. So again, just a description of what I will say. It's very common records I'm talking about. The origin of the noise is well understood for the global oceanic noise, meaning that in the period of so-called macro seism, we know what we are talking about. I mean, the physical origin of this noise. Of course, the interpretation of the change we can measure, and we will see that we have limitation on the type of wave we can use, is not trivial, and we have to continue to think about. But it offers a chance to observe important events in a reasonable time. Because of course, you have access to all the network all over the world, and there is somewhere an earthquake that is initiating today, and this is the one we will be able to use if we have the good tool. So the idea is simple. If we have this correlation that correspond to the records from station A to station B, we just expect to use the correlation of the noise and to compare different periods in which you compute this correlation. And then you expect that, for example, the position of the source does not change in the story. And the noise is relatively stationary, so you can expect also that the source itself, this mechanism, is not changing. And so the issue is then we would like to compare this two-point correlation function before and after an event and measure the change of velocity. I will talk about change of velocity, but it's not the only things you can measure. You can also, we will see, measure other parameters. We can think about attenuation, scattering power, and this is things that are also used and possibly done. So, the shortcomings. The stability of these two-station correlation in time depend on the change of the actual source of ambient noise. So if you take very long time period, you expect that you will retrieve the same result, exactly, even without change in the medium. But you know that the noise has, for example, obvious trend of seasonality, meaning that clearly the record of the noise we have here in Roma is changing between winter and summer. The waves in the macroseism band are completely different, coming from different directions and so on. So if we consider if we look at the direct wave, it's clear that there is a bias that exists that is related to this change in the nature of the noise. It has been studied, it has been quantified, and we know the amplitude of this bias, for example, between summer and winter. And it's due just to an integral over the angle of the different sources, and the weight of the intensity of the waves is different. So there is a bias. And it's small. It's small enough to allow for imaging, but it's not small enough to allow for monitoring. By chance, the stability is much better for multiply scattered wave, for the coda. And the theory and the numerical simulation show that we expect that even if you have big change in the distribution of the noise sources, you will keep the velocity, the apparent velocity you measure in the coda in a range of relative change that is of the order of 10 to the minus 5 or 4 with the typical situation we have. And this is due to the idea that there is no more geometry implied for most of the paths of the multiply scattered wave because the scatterers are not moving. Of course, this is true if the scatterers are not moving. But in the Earth, the first order, the scatterers are not moving. The main scatterer that produce the coda wave. And so in that case, it's much more stable. And we can make a test, and the test is with data from Japan, where we have this large network, and we did exactly what I mentioned here. So we compute all possible cross-correlation, and we will just show the variation of the apparent velocity relative as a function of time in this story. You see that it's a big data set, and there are some work to do, because here in Japan, for the period we study, we end up with 10 to the 10 billion of interstation correlation function. And we have this image here. And with this image, you can see right now that the value of the relative change that we observe at this date is 92 days before the Great Tokyo earthquake. You see that with the color bar, that the fluctuation we had up to this date is of the order of 10 to the minus 4, less than 10 to the minus 4. And this is very stable for a long time. And what happened during the earthquake, you see it's much, much larger. So this is a good example where you can see that during the period, the pre-earthquake period, we measure very stable velocities. And that what happened during a period as a change of the velocity inside the crust is actually much larger than this level of fluctuation. So this means that we can use this type of measurement in the CODA to make the monitoring. Again, there is a drawback. The drawback is that you have to use CODA waves. And CODA waves are a little bit more subtle than direct wave to make the monitoring. And with this technique, we know that we can detect things like earth tides in the variation of velocity, and there are different examples of that. So the capability of detection is very, very good when we use this scattered wave and a network that is just distinct station in that case. There is no specific array processing done before. What you find in most of the paper is the assumption that there is homogeneous change of seismic velocity. And in that case, you have a very, very simple relation that has been discussed, you see, in 82 by Poupinet and co-author, that if you have a change and you look at the wave that has been beautifully scattered in the medium, you will have a delay between the two signals that is linearly increasing with time. And so it's very easy. If you measure the DT in different time window, you can plot the delay as a function of time. You have a slope, and this slope is a constant. It's a constant, and it's easy to show that is minus the relative change of velocity. So you have a direct measurement of the change of velocity. And it was called the doublet method at this time. And they apply this by assuming that they have exactly repeating earthquake. But typically, it's what has been mostly used. Now, one of the questions, and we will come back to it again probably, is the question of the depth of the change in this wave. So what are the dominant wave in the CODA? This is an issue that is telling what is the part of the crust that is sampled by this CODA wave. And there are different results, recent results, that allows to be relatively sure of the fact that if we look at the sensitivity of a layer at different depths as a function of the lapse time in the CODA. So, and we have numerical results by Annals and co-author that are based on full 3D elastodynamic computation. And we found that making tests, that is inverting the observation by putting a partition coefficient between what is the weight of the surface wave and what is the weight of the body wave, we obtain this curve here. This curve here, in which you see that the weight of the surface wave is very large at the beginning and decrease with time. And of course, the weight of the body wave is the opposite. Now, the scale that is here is important because what is the measurement we are making when we are talking about the CODA, before to be into the real noise, is the fact that we work usually with the early CODA. And this was the numerical guess. And then there was some theoretical results that has been made from theoretical consideration, not optimization of interpretation of numerical results, that lead to this curve. And these curves are the same, and I just realized that, of course, the color are inverted. It's just to produce some confusion for you. But the theory is the numerics are leading to the same conclusion. And the same conclusion is important for the following is that it's a good guess, a good assumption, to consider that the early coda is, in terms of sensitivity to a change, is dominated by the surface wave. This is what we will do. But now we have this theory, so we are building kernels that are both surface and body waves. And I think it will be the next step for us in the next year. So I told you the simplest way of interpretation that has been followed in the last year, that was surface wave, homogeneous distribution of the change. Of course, this basic assumption does not make really sense. The one on the homogeneous variation of the velocity. And it's a big issue, because if you consider a case where you are a finite size region where there is a change, that is the pink zone, and you consider the extent of the development of the coda wave, you see that in that case it will be perfect. You will see that dt over t is a constant, so you are really measuring the relative velocity. If you consider the coda wave at a later time, you see that the coda wave are actually sampling a region where there is no change. And so the apparent change is actually decreasing. And so what you expect from this situation is that the true curve will be this one. And so our hypothesis is seriously wrong, and we get a value, and the value is nothing. In fact, if you think about the problem, the value could be really a problem. And I would like just to show you that we need to make a first effort here. That's why I say it's not fully trivial. That now we should take into account this geographical change of the velocity. And to do that, we have to use an imaging type technique, that is to have an inversion to relate this change of this delay with the lapse time and with the space. And so there is a problem that we can write, and this is presented here very rapidly. When we have two stations, we have at a given lapse time, we can write a linear expression that is linking the change in the space with what you expect at this given time for this specific lapse time, for these two stations. So in a given time, you observe all the waves that find paths to go from this source to this section. And these waves are passing in different places. Of course, here it's a simple drawing. In fact, we are talking about multiple scattered waves. And this is what you need to evaluate if you want to relate correctly this change in the medium with this change of time at a given lapse time. Of course, this equation you can write for all lapse time. If you know the kernel, and you see that you have the dV over V at all points. So it's very similar to an traditional imaging inversion. And if we do that, we can get rid of the problem I just mentioned before. So we do not know all the details of the story, but we need a model to explain this. And to do that, we will use models of coda energy that are based on the radiative transfer theory. And I have a slide to explain you why we need to do that to have a decent kernel. And I was not willing to be long or or too boring, but I think it's a key issue. It's a key issue that has been solved, in fact, by Ludovic Bargerin a few years ago. When you have a station here and a station here, this one is a virtual source, and we want to evaluate the sensitivity of a point that is here. What we have to keep in mind is that even if you make a guess of isotropic scattering, the field itself is not isotropic at all. At the beginning, of course, just after, at the time of the ballistic wave, is completely forward. And then the distribution of the waves at a given point are changing progressively to end up with, maybe for a long time, to an almost isotropic, diffuse wave field. But what is important is that what you need to know is what is the energy that is arriving here in a particular direction. And in the same time, the form of reciprocal problem, how this direction will actually produce energy that is at the station you observe. And to do that, you use this time reversal thing. So you use the backward specific intensity. So you see that if you are backward, you have just to turn the direction, something coming in that direction, or going in the opposite direction, and you realize that what is important is the product of these two functions, specific intensity, that is the intensity in given direction. At the end, you have to integrate over all directions to get the kernel, but you cannot get rid of this anisotropy of the field, or your result will be relatively wrong. And if you do that in the simplest case, you get a simple result. And the simple result is seen here. You see for different time what is the sensitivity kernel for the 2 points that are measured here. So you have a source and a station. And you see that it's quite simple. There is a region of interaction for which you have a sensitivity, and you have a strong concentration around the station that is very logical, because all the waves are passing to the vicinity of the station. So there is a clear sensitivity at this point. So we have this type of kernel. And the first type of things you can do is use this kernel to do application in which we claim that we can measure more precisely the amplitude of the velocity change. And this is an example on a shallow process, because these techniques are used for environmental studies more and more. And this is a work that is by Chujuan Mao. And it's a study of the Los Angeles basin, where there is the drought for a long time, and the velocity that is measured on this array, that is not made for that, it's the regional array, and are showing that there is an increase of the velocity that can be interpreted like a decrease of the presence of water in the sediment. But to try to quantify this, what Chujuan did is that she used monitoring of all the stations of possible pairs and imaging using simple kernels. And she got this type of result, where you see that there are changes that are localized, and they are clearly localized in the basin, where effectively we expect to see some changes. And here, something that is interesting is that you have different frequency, and because we have said that it's surface wave sensitivity, the sensitivity change with frequency, and the sensitivity is deeper and deeper when you decrease the frequency. So we have different depths, in fact, and at these different depths you see that there are quite different distribution of these changes. While here you have the INSA observation that is showing that there are vertical motion in the basin, and you see that the interest of this type of technique here is that, of course, the INSA is integrating the change at all depths, and with seismology you have a chance to decipher the change at the different depths. But also, because you are doing properly, even the average velocity, you can measure it more precisely, and you can study the average change and look at the relation with the precipitation. So you see cyclicity of the annual changes and the response of the basin in average to the precipitation and the reloading of the sediment by water. And when you take a local comparison of what you obtain by your inversion of delta V over V with a measure of the hydraulic head, the depth of the water, and you obtain this curve here that is showing that it's a very efficient way of monitoring the change in the water content in the shallow layer. So I think it's a clear test, and in the same time it's a very useful for environmental study. So let me continue, and these environmental effects are known, in fact, in terms of the velocity of the seismic wave. We know that there are the drop of velocity after big earthquake because of the nonlinear response to strong motion. We know that when the water level is close to the surface, we see some change of velocity. But here we can quantify, we can localize, and of course we cannot get rid of that, because when we are considering deeper target, the waves are passing through this shallow layer. So we can keep in mind that there is all this side of environmental studies, but even for more tectonic-oriented studies, earthquake source, things like that, we cannot get rid of it. We should take it in account in our interpretation. So, but the big question that has been raised by several people is, do changes occur at depth? Is there something to look at? And I would like just to first to remind that we are evidences for deep change for different cases. Some large earthquake, including Tohoku. I will show you something about Tohoku. It's also observed during slow slip event, and we just very rapidly see an example of that. But first of all, we have observation that are below all this critical zone with the water table and so on, just in mind. And I just want to show you this example because we are in hard rocks. We are at 1 kilometer depth, and there are big arrays of seismometers that are running in this mine for security problem. They use the seismicity as an indicator of the risk of collapse, and so it's their data. And here there is a series of blasts to open a new tunnel, and we have stationed around, and you see that there was seismicity in the same region. So it's a particular problem. We are at depth. We are in a mine. That means that it's extremely noisy. You have machinery everywhere, and you have tunnels everywhere. So it's highly scattering medium. And if we go directly to the results, we can look at what happened for the change of velocity at the time of the blast. And the blast is at the red vertical things. And you see I drank too much coffee in Italy, so okay, you see that there are changes that occur that are also the noise of the measurement and things like that. But at the time of the blast, you see there is a strong velocity drop in the region. And strangely, if you wait, you see that the velocity pattern is not coming back to what it was. There is a clear change with region of decrease and increase of velocity. And we can understand this in the context of first, the fast dynamics, the fact that there is this nonlinear elasticity that produces the drop of velocity. After that, you have a relaxation that is coming, that you expect, and there is something else. And the something else is that here you have side view and plane view, side and not slide, side view and plane view, and you see that at the time of the explosion, there is this big drop of velocity. But after some time, you observe this distribution of velocity change that you can compare with the static stress change due to the digging of the tunnel that has this shape. And so you see that we typically, in a hard rock massive, the velocity is affected both by dynamic damage and keep the signature of the strain change. And this is a direct in situ of what we would like to observe in practice. So now let's look deeper. To look deeper, we will look at longer period. And here we use the tilt meter of INET. You know that for each station there is tilt meter, and this tilt meter has been used as long period seismometer, and we use these things. And this is two maps. One map after the earthquake, sometime after, and one is in the 1 to 7 second, and we observe that the maximum velocity drop is really limited to this region here. And if you compare this with the PGV, the peak ground velocity, you see that there is very good correspondence between the two. So there is this effect of nonlinear elasticity after a very large earthquake, and there is a correspondence with the PGV. When you go from 1 to 7 seconds to something much deeper, 8 to 30 seconds, you find a map that is different, because you see that it tends to be more in the north, that you observe the decay of velocity. And yet this you can compare with the dilation, the model based on the slip model of the Turku earthquake, and you have the same thing, the same geometry of difference between the PGV and the dilation. So this are indication of one, that maybe we see the same thing as we have seen in the mine, but also that it's different when you look at different frequency band. That is an indication that we are really measuring something that happened at depth. And just to make the point, if we consider the evolution in time of the velocity with different frequency band, we observe that the shapes are different. And if it was just the surface effect that is smeared to the depth because of the sensitivity kernels of the Rayleigh wave, we would see the same curves. And we do not see the same curve. And if you consider the effect of the shallow layer as the one that you see in 1 to 7 seconds, and you compute what you expect for 8 to 30, you will get something much smaller. So there is something specific in the middle crust and in the lower crust that is occurring with different history just after the earthquake. And I will not, I have no time to go to the details, but this is where we are. And now we have the same for the slow slip event. For the slow slip event, we observe change of velocity. Change of velocity, just to be very fast, here you have several years. We are in Mexico, probably with a station that we installed with Massimo a long time ago. And this is the slip that is obtained by inversion of geodetic data and compare with the evolution of the velocity here. And you see that there is a very clear correspondence. And these data are measured in different frequency. And if you make the inversion, you find that the change cannot be at the surface. It can be only in the lower crust or below, because you have no clear resolution at depth. But it's a clear evidence that there are changes of velocity in the lower crust that can be measured during the slow slip event. And this is the type of things we can do, and I hope that I convince you that we can really monitor at different depths. Now, again, drawbacks and a little comment on one of the problems that are interesting us, that is monitoring faults or volcanoes. And in that case, what is clear is that there is a non-uniform scattering. You see, we are starting with very homogeneous models, and then we have to go further in the complexity. Non-uniform scattering, because the fault zone is a zone of damage where the scattering is larger. And of course, same for the volcano, where we know that the scattering of seismic wave is very intense in the volcano. So I took the example of the fault here, and just this figure showing that the San Andreas fault show a low velocity region at depth, and that is interpreted as the presence of this damage zone. So now imagine we make a small experiment with what I have shown you before. What I've shown you before, there was not such a big difference, but here we have a model in which we have only 8 stations that are used. We have a fault zone with strong scattering and a velocity change in the fault zone, and we are generous, we put 10% of velocity change. Can we retrieve this from the inversion of the data with this 8 station? We use a sensitivity kernel that neglect the strong scattering, and we obtain this result. I would say, great. we detect that there is an anomaly somewhere in this fault, but it's a numerical test. And you see that what we found is that the change of the velocity is much smaller than what it is, because it's smeared, and you have even a change of the sign of the change outside. So it's not working so well. Can we do something to improve the quality of the reconstruction inside the fault? What we can do is to, and it's maybe here that you will understand why I was insisting of this story of computing correctly the kernels. We took now a model in which there is this scattering band. So, and we compute a new kernel. And this is the kernel. You remember the simplicity of the kernel before. Now, let's look at what happened in something that is more looking like the real world. It starts the same way, and then there is the interaction with the fault. And there is this complex pattern that occurs. And that change with the elapsed time. And you see that there is some propagation of the diffuse wave in the scattering region. So you see that we have completely new completely new pattern that appear when we take into account the scattering. And we have something quite similar for a localized zone that corresponds to a volcano. And in that case, even with the 8 station, when we do the linear inversion, we retrieve almost perfectly the distribution. Meaning that there is another step to add, that is to know more of the scattering property than we know today. And I claim that it's also possible to use the code envelopes that we have and specific kernels, not for the time, not for the delay, but kernel for the amplitude. And then we can retrieve first the scattering structure and then have the monitoring running with this information in hand. And okay, this is what we are working on now. So now I will have to go fast because I have still some time or not?
You still have 15 minutes.
5:15, 10. Okay. Okay, no, so first of all, here I was completely focused on Coda waves. It's because I think it's important, but it's also my own self-focus aspect. But I would just want to show you that there is other type of monitoring you can do. Here we have, we'll take an array data and we will compute the correlation of noise, assuming that we are generating this virtual seismogram that have the sense of the grain function. And we will use an array technique to beamform the signal at depth in order to detect the scatterer, to have an image of the density of scatterer at depth. We can do that. The problem in the Earth is this issue of the lateral variation and multiple scattering, for which you need a technique of adaptive focusing. And we use a technique that has been developed also in optics and acoustics, that is called the matrix framework. And I will not explain in detail because it would take a lot of time. And but you imagine the story of improving the focusing. And we are going to geothermal experiment in Finland that has been extensively studied by Quitec and others. And it's a 6 kilometer deep experiment with injection that actually trigger a series of earthquake here. And as a function of time, there was absolutely no earthquake. The start of the injection, earthquake. At the end, the seismicity stopped after a few days. So it's a simple thing. So if we consider now what is the scattering structure before, we get an image, and the image at this depth is given by this structure here. So, and this structure we found was actually this dipping structure was identified before from the VSP by Akinen and others, and we retrieve the main structure that has been described in the previous studies, just with noise during a short period. And I do not show below because below there is the problem of the P to S conversion, and so you have mixing of S in this technique. After all the process, stop of the seismicity. So I cut the question on the effect of the seismicity. There was no seismicity at the beginning, no seismicity at the end. And this is what we obtain. The scattering structure has changed significantly due to the injection and on a scale that is much larger than the extent of the seismicity. And the interest of this type of technique is that we can do it by a time-dependent imaging for each of the periods that are indicated here. We have a different image of the scattering, and you see that this is extremely stable. For example, at the end, we have this clear stabilization of the structure. So it's interesting. We can look at the detail. We can make some analysis, and one of the only one that I would show is just the interest of trying to measure the direction of extension of this scattering structure. And the direction is what you can see here. The direction in the different time is actually in the direction of the maximum horizontal stress, as expected. But this means that we could really see what happened at depth. So it was short. And my last part, so it will be shorter, but I would like just to show that the use of identifiable isoentropic sources and dense array. We will detect tremor-like signals from train. And it's a group of, it's work by the Florent Braguier on this group. Then you use a dense array to characterize the ambient noise. You identify specific path in the two station correlation, and then you can extend the analysis to long term. I show it rapidly. We are in California, San Andreas, San Jacinto, and they installed this array with 300 3-component geophone, and they are recording. They are still recording. No, they are no more recording. They get back the station last week, and all the data, by the way, are available. And you have also broadband stations in the region. So what they found is that there are this passing of this heavy freight train in California that are producing these beautiful tremors. They are so beautiful tremors that they have been considered as non-volcanic tremor at a point, but in fact, no, it's clearly the train. And this train can be recorded and used to look at the correlation between different stations, and especially what you can do is to use the array. You can use the array to track the direction of the waves that are passing. And these correlation functions, of course, are much simpler than the tremors. There is a form of deconvolution. And you can observe, for example, clearly this dominant arrival here that is a P wave, and this is the corresponding with this particular path here. So you have one station and the array. You compute this. You have the array. With the array, you can analyze exactly the velocity, the apparent velocity. So you can identify the path, and you say, okay, it corresponds to a path that is at depth below the San Jacinto fault. And this is what they did. And doing that, when they know where it is exactly in the correlation, they are able to consider now long term by taking this correlation function between permanent station, and before you are unable to understand what are the different signals that you observe in this correlation function. Now you know where exactly is the P wave, and doing that you can extend your analysis for a long period, and during this period they found that there is a clear event that occurred in 2014. So there is a change of velocity along this path. Now they did the same with other stations, and they found that the results are changing with the different station. That is actually interesting because they found that there is places where there is a change of velocity that can be negative or positive. And they suggest them to make a model to explain this change by a slow slip in the lower crust and the strain effect of the slow slip in the lower crust that actually explain this distribution of velocity change. So it's really an opportunity study. I mean, you really take all advantage of the actual noise, even if it's train. Train are good because train are always passing at the same place, so it's good. It's a good stability, but it shows that it's possible to do interesting thing with that. So I don't ask you. I will not come back to the recap, but just to say that I think we could do passive seismology to help in the understanding of the dynamic of the crust in a complement to what we have. And CODA-based 4D imaging is not trivial, but it is on its way, and I hope maybe some of you will contribute to that. And huge data sets are available and waiting to be processed. We can also use noise correlation to use body wave with some limitation, not dV over V. I did not speak about dV over V because it's not so stable. What is stable is the rough position of the scatterer. And also opportunity are numerous probably to get interesting result as the one that has been shown by Bragi and others. And I would stop, and I'm sorry to be late.
Thank you, Michel. Thank you very much for your presentation. Just a reminder for those that are that are following the presentation in streaming, you have received a link to a shared Excel document. Please include the questions, if any, on the file, and we will read the question and repeat the question for Michel. This is particularly for those that are following streaming the seminar. So are there questions for Michel? Who is first? Luca first.
Thank you. Thank you for the seminar. It was great. And I have a number of questions, actually. I will start with the last thing you showed was the I'm kind of intrigued of the 2014 jump that you show us, and you said there was an event there, and I saw something similar happening at Parkfield, and the time was the time of the Napa earthquake, which is far to the north. Do you know what is the reason for that jump?
So it's a work by Bragi and his postdoc, in fact. So I can the reason that they claim is that there was a transient of deformation because this will produce a change of velocity of opposite direction between the zone of stress drop and the outside.
So that was a local earthquake.
A local earthquake, yes, at depth.
Okay.
But it's the effect of strain. It's there is no big earthquake. They claim that there was a deep transient. So
Yeah, the same thing happened at Parkfield. After the Napa earthquake, there was an enhanced activity of the known volcanic tremor below, and then fluid were probably coming up, and also they changed the attenuation at the surface. So I don't know.
No, maybe it's the same type of things. Yeah. Deep origin.
Okay. Can I ask you some something else. I saw you showed a picture. You have water level and velocity changes at some point towards the beginning. I don't know if we need to go back to that, but I saw there's a clear phase difference between the two curves that you.
No, I missed.
I think it's.
Yes.
Yeah, that thing. There is a phase change, so between the water level and the velocity changes.
Yeah, you mean?
And that's typical also if you see attenuation changes and water level, or at least attenuation changes and the amount of water that is in the aquifers. So deep aquifers here are in summer, and then they get depleted in winter. So there is a 6 month phase delay, and so the attenuation goes the other way around. And so I was wondering if that is also related to change in permeability or change in because the increase of water and snow load and the increase of the amount of water you have in the deeper aquifer changes your permeability because you increase the pressure of the fluids down below. Do you have any explanation like that for this?
Sure, physically there are different processes in the same time, and even the humidity in the first layer is changing. The water level here, but something in this region that is dominating is the pumping.
Is what?
Pumping of the water is Los Angeles, so they are pumping as crazy in the. So the it's not the classical physical process of during the summer, for example. There is a very strong pumping, and
so there's a seasonal variability also in the pumping.
Yeah, also of the pumping, and because in this region here it's the Santa Ana, so it's the Orange County. They are pumping back in the winter, so they are really do a lot of engineering. So it's why I think that the physical analysis is a bit more difficult to do. And maybe it's why the level is so well retrieved also. Because there is no much other interaction in it.
Can I add one more thing? One more thing. Same kind of topic. I saw your little movie about the Tohoku earthquake, and then you show results at 8 to 30 hertz to 30-second periods. Yeah. And then the PGV is like related directly to the dynamic strain, and it's the precisely the what changes the crust of permeability due to the breakage and removal of colloidal deposit in cracks. And so how can you say anything about changes in permeability?
Now, what we can say is that when we look at this curve here, you have Tohoku earthquake here. You have the relaxation at the surface, and then there is this second drop here, and you see it's not a strong jump. It's a relatively continuous drop, and we spent some time with Jingyu Wang to try to understand what it is, and we look at the seismicity, we look at the whole environmental aspect, and it's something that is generalized in a large part of the North Honshu region, and especially in all the region with volcanoes. And we try to understand what would happen here, and looking at the intermediate frequency band, also, we found that there is a delay of this jump that is starting below. So a possible interpretation would be that, in fact, the effect you are mentioning in the deep crust are associated with upgoing fluids. At this time, we start to see some deep, long period earthquake, late after the earthquake, and eventually reach the surface region. And in this interpretation, it took something like 10 months for the flow to diffuse through the whole crust. So possibly there is an effect, and the first there is what you say about the effect of the shaking, but the other effect is that with this earthquake there is a strong extension of the crust, and the two probably together could explain why it helped the fluid flow upgoing.
Thank you very much.
Thank you, Luca. Claudio?
Thanks, Michel. Very interesting how this changed our perception of the Earth. And according to your experience, the amplitude of the change of velocity you observe, is there a possible limitation in such values from the computation itself, or it's also maybe related to the different period that you are using? If this can...
I think one of the issue in my response is the assumption of the surface wave. Because with the surface wave, when you are going deep, you are going at long period, and you are losing all, the wavelengths are very large, and so you have no resolution, so you are averaging everything, and if you have a region of strong changes, you will average it. So, but now we would like to use an interpretation in which we use both body wave and surface wave, and in that case we expect that maybe we will see more localized effect. We have a limit of the size of what we can detect, and this is this question of the effect of the non-stationarity of the noise, and this is a true effect. I showed that the limit is very low, but the limit is there. So there is a point where it will be very difficult to go further. You can imagine to do more clever things by doing more pre-processing of the data from the beginning, from the raw data. We were thinking of using some technique of signal classification to try to improve the stability of this measurement. So there are things to do. So there is a limit. But on the other hand, we measure the tides on arrays. But we measure the tide, except in some specific places, but in general. And so measuring the tides is already opening a way to, I don't know if you have seen this recent work by Eric Bosset. He was looking at the seismicity, the dependence of the seismicity over the tides, and he found that this sensitivity to the tides was increasing before the Ridgecrest earthquake. Actually, a similar observation has been done in Japan a few years ago. I do not remember the author, but there was already someone who tried to do that. But that means that if you are able to measure these non-linearities with respect to things as small as the tides, it would be very interesting, because in the let's say nucleation initiation phase before the earthquake, you expect in fact the damage to increase, because the damage is the expression of this preparation, and so in that case the sensitivity would change. So this next step would be to use the sensitivity of this effect to do time-dependent analysis of the more subtle mechanical state of the crust.
And the follow-up of your, do you think that there could be some kind of improvement in monitoring, instrumentation of infrastructures around faults or volcanoes that we need to go further, or what's your point?
At least in terms of instrument, what is clear is that what we call now noise in seismology, in most of the case, it's not noise; it's physical vibration. So for this, we are really okay. Most of the network are good in terms of time. So I would say, yeah. After that, there is the quality of the installation, and that are very different. And there are, when you play with this correlation, you find very strange things. I mean, you try to make correlation. I give you an example, but we try to make correlation between station in Europe and station in Japan. So we did that, and we look for specific deep phases. And at a point, it appeared that we have very good results. So the student came and said, yes, you see, this is... I say, okay, look at the other station around, so we can measure the apparent velocity, we can be sure of your interpretation. It did not work. And so we start other measurement of correlation with the different station, and this station was working perfectly well. And it was the same, it was the FNet network. In principle, same installations, everything. And then I have a discussion with this guy from the Black Forest Observatory, our German colleague, who is a really specialist of very long period installation and everything. And I asked him if the stations are the same, and he said, well, they are the same, but this one is much better for the long period. So actually what we observed is that this station was really good in the sense of what we expect. That probably no local effect, no thing like that was contributing. So the installation is very important. There are still a lot of things to do to improve, even if we do not understand always why. But
yeah, thank you, Michel. So there are some questions from Paula. There are questions on the board? No. So if there are questions, I have a question, Michel. Actually, that is quite general, and two questions actually. The first one, you have interpreted the results of the change in the velocity using different phenomena. So, but at the end, could we find a common process that is driving? Is it strain, for instance, transient in strain? Because it is not the amplitudes. And also we refer to damage, but damage is only a way to change the properties of the medium. So which is the guiding process? Is strain. Is this correct or not?
Strain, but you have to add the presence of water, because it's make a big difference if wet or not. And the issue is that in this damaging process, it's like in all the friction models, the history is important. So it's difficult to expect to see something very simple that you can apply, because the history of the material is important.
Yeah, so this means that there is a memory.
Yeah, there is a memory. We see on the fault, there are mature fault and so on. So there is a memory of the deformation, and we have to, so I don't know what to say, but we know that it will not be so simple that we can...
And this came to the second question that actually is very theoretical, perhaps trivial. So here we are measuring variation of velocity. However, our definition of wave velocity is zero level, so it's the first approximation. And we know that even the definition of the wave velocity, so there are two models, and for instance, the model differs for the way in which you define the crack. If you have elliptical crack or circular crack, at the second order, the P wave velocity, the S wave velocity change, the theoretical one. So in a medium that is so complex, are we sure that we are measuring the velocity with the proper the proper definition?
I would say that first of all, we do not measure the velocity. it's too difficult. We are less ambitious. We measure the relative change, and relative change is much simpler because you don't not care about all the difficulties. So the crust is we are measuring effective velocity that are also anisotropic and everything, of course. But we just concentrate on some relative changes. So it's my answer. We are looking at relative changes, and then can we go further? It's difficult. Also, it's a drawback of using a coda wave. Is that, for example, coda wave are propagating in all directions, and waves arrive at the same point while they have propagated in different directions. So a signature of anisotropy would be difficult to observe, in fact, in the deep part.
Yeah, because this question came from my past experience in measuring stress changes with varying poroelastic properties of the medium. And actually, when you define the compressibility parameter for wet, saturated, or undrained materials, it has an effect on definition of P and S wave velocity, and also in the rigidity, in the ratio. So I really wonder how much are we capable to really follow and measure the properties of this media when we arrive at this level of small scale changes of
if you observe the change in the effective velocity is what we can say. To go into the details of the change, you could have some clue by looking at the frequency dependence, because in the model you mentioned there is a frequency dependence. So maybe if you have a sufficiently broad frequency, maybe, but we are not there.
Yeah. But by the way, one message that I take from your presentation is that also in Bedderetto for fear we must do some noise correlation, because I'm pretty sure that the properties of the volume that we monitor change also for environmental reasons, maintaining the stress heterogeneity. So this makes me a bit difficult to understand what does it mean, the preconditioning, because the strain state of the volume is not constant at all. So we don't know which level of heterogeneity. We must do something for that recordings, I think. So are there questions, further questions? C'è niente da... Okay. Okay. So I thank Michel. I am also happy that you remembered the collaboration in Mexico City, because actually I forgot to tell when I introduced Michel that Michel, I think that we had the first European project of ING. V does not exist at that time, because it was FP2 in 1992, and we were deploying stations in Mexico City. So for my knowledge, is the first European project of INGV. And Antonio Rovelli, with myself, that was a young student, I was working with Michel with this deployment. So that's just to corroborate the long-lasting collaboration that Michel has with INGV. Okay, thanks again.
You can leave all your stuff here.
Okay.
We have a lunch just outside the room conference.
Ok. Et alors, tu
Ça va? Je vais bien, et toi?
écoute, ça va.
T'es pas à la retraite alors?
Si, je suis à la retraite, mais je continue à faire ce genre de choses.